Hi everyone and welcome back to our YouTube channel. In this lecture, I will show you what a homogeneous system is and how we can find a solution to such a given homogeneous system. Alright then, let's start with the definition of a homogeneous system. And here is the definition. A homogeneous system is actually a special case of system of linear equations where we have all zeros on the right hand side of the equations. In other words, we have an m by n system. In other words, we have m equations and n unknown variables, and we have zeros on the right hand side of all equations, as you see. So as you notice, I just circled in red, these values are all zero. And which values are these? These are the values on the right hand side, okay? And again, our coefficients are still the same. We have the unknown variables, we have the coefficients, so aij values are again real coefficients values, and these are the coefficients, right, as we are familiar with, and these are the coefficients, and xi's are the unknown variables. Okay, xi values are the unknown variables. We have the same unknown variables here, but this time what makes a homogeneous system different from that of we are familiar with is that we have all zeros on the right hand side. And before even diving into the details of how we can solve such a system, let's start with a very simple observation. Okay, one simple observation that we can make is that even without computing anything else, we are ensured that at least we have one certain solution to a homogeneous system. And what is that value? So first of all, we know that actually we are looking for a solution in the form of an n tuple, right? So since we have n unknown variables, actually what we try to obtain is just an n tuple of these unknown variables that satisfies all of the equations given in the system simultaneously. So one absolute solution is that suppose I take all the values equal to 0. You see, if I take the values of all the unknown variables equal to 0, then what we have? Does this tuple satisfy the equations at the same time? In other words, I have an n tuple which includes only zeros. And our answer is yes, that absolutely satisfies all equations, because when we plug the values of unknown variables all equal to 0, and then what we get in each equation, we have something like 0 times coefficient, right? 0 times a11 plus 0 times a12 and blah 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 plus 0 times a1n, and multiplying any coefficient by value 0, we again have zeros, right? So, and summing up all the zeros will yield us again a 0, and surely each equation would be satisfied by the selection of the unknown variables equal to 0. So if we take all the unknown variables values equal to 0, then we are done. We have one certain solution, and this solution is called, or what is known as, trivial solution. So this is the trivial solution to any homogeneous system. Okay, but of course what we are interested in is that finding solutions which is not trivial, and those solutions or the solution sets are called non-trivial solutions. And a non-trivial solution is again a solution that is different than 0. And by saying 0, I mean different from what I mean by saying different than 0. In other words, at least one value which is not equal to 0. The value of unknown variables, of course. Okay. So the trivial solution is nothing but the solution where we have the values of all the unknown variables equal to 0, and the non-trivial solution is something different than the 0 solution. Okay, and what we are interested in finding is this type of solutions, a non-trivial solution to the given system. Okay, what are these? Otherwise, we already know that we at least have one solution to this homogeneous system. Alright, so now let's get to the real point. Okay, so how we can find solution to a given homogeneous system. Alright, then I will again give you a step-by-step procedure, well, call it an algorithm, that we should follow in order to produce the desired output. And in this case, our output is the solution set to this given homogeneous system, and our input is that arbitrary given system, right? And n by n homogeneous system is given to us. Okay, so the first step, before even giving you the steps of algorithms, or in other words, a sequence of instructions that we should follow to find the solution set, let's write down an example and work on it and apply its steps on this system. Okay, let's say we are given this system, say 2x1 plus 4x2 plus or minus, say minus, that doesn't matter, I just make up values, so 6x3 and say 2x4 is equal to 0. Suppose this is the very first equation given to us, and let's continue. Minus 4x1 plus 2x2 plus 4x3 and plus 2x4 is equal to 0. This is the second equation, and let's give one more equation, say minus 2x1 plus 6x2 minus 2x3 plus 4x4, okay, is equal to 0. Now suppose we are given a 3 by 4 homogeneous system where 3 represents the number of equations and 4 is the number of unknown variables, and we are asked to find the solution set to this given homogeneous system. In other words, what we are trying to find is the 4 tuple of x1, x2, x3 and x4. And again, even applying any technique so as to find the solution to this given homogeneous system, we know that we have at least one certain solution which we call trivial, right? Which is nothing but taking the values of all the unknown variables equal to 0. So if we have 0, 0, 0, 0 for zeros, that will satisfy each equation, right? Because multiplying by 0 yields us a 0 on each side, and summing up all the zeros again as 0, and each equation is satisfied because 0 is equal to 0. This is always satisfied. So nothing to do for us at that point. So what we are trying to do is, actually we will try to find the non-trivial solutions, okay? So let's get the show on the road. So the first step we should take is what? As usual, actually, we need to first represent the given system in the matrix form, but this time we will not represent our system in the augmented matrix form. Rather, we will represent our system in the coefficient matrix form. So the first step is that represent our system our system in the matrix form, and this time in the coefficient matrix form. Coefficient matrix form. And why is that? Well, now we'll get to that point. After we write the first step, let's now see why is that supposed to happen. Okay, suppose we write our system in the coefficient matrix form. This is 2, 4. I write in the first row, again I write the coefficients of each unknown variables along with their signs. Don't forget negative signs as well. And for all equations I repeat the same process, -4, 2, 4, and 2 again. And for the third equation we got -2, 6, -2, and 4. Here's the thing, guys. You see, I didn't represent our system in the augmented matrix form this time. Rather, I preferred writing our system in the coefficient matrix form. Why is that? Because suppose I represented it in the augmented form, then what should I do? Then I would have written zeros in the last column, and as you remember, the last column actually corresponds to the values on the right hand side of the equations. But the thing is, performing any elementary row operations in the following steps wouldn't change these values at all. In other words, multiplying 0 by a real value is again a 0, and summing up all the zeros or some combinations of zeros would yield us again a 0 value. So it is, in other words, we just save space here. We don't need to write the last column here, because that wouldn't change the result, right? Zeros would be again zeros, but we know that they are there. So I don't need to write the very last column here due to this reason. So I just erase it. Alright, and I use the coefficient matrix form. This is the first step. So to solve a homogeneous system, the first thing we need to do is that just represent our system in the coefficient matrix form. And let's get to the second step. And the second step is that now, here's the second step. By the way, let's give a name to the matrix we just write above. Let's say A, okay? Let the matrix be A, okay? Just give a name, okay? And the second step, what we need to do is we reduce this matrix into either row echelon form, and in short, in capital letters REF, or reduced row echelon form, if I abbreviate it, as you see, okay, either by using Gaussian elimination method or Gauss-Jordan method that we're familiar with. Alright, so this is the second step. In the first step, I have my matrix representation, and in the second step, I need to eliminate this matrix. In other words, I need to turn it into either row echelon or reduced row echelon form by using a technique, either Gaussian elimination or Gauss-Jordan. Let's start to do that. So in the second step, alright, then what should I do? Suppose I preferred applying Gaussian elimination method, so then I need to convert my matrix into the row echelon form. And the first thing to do is, okay, I need to have strictly increasing number of zeros starting from the top row and ending with the last row. So the first thing to do is replacing row 2 and replacing row 3 by something else, by performing some elementary row operations. Okay, so for the row 2, say row 2 plus, so we got -4 here, And the thing is that, the first pivot element, as always, I look at the first row and I see that the very first non-zero element in the first row is 2. So this is my first pivot element. And I need to eliminate the values below this pivot elements. So this -4 and -2 should be zeros. Alright, how can I do that? So, okay, the way to do so is that multiplying row 1 by 2 and adding it to row 2, I would obtain the required result. And for the row 3, what I should do is that R3 plus R1 would give me the desired result. So my matrix, my new matrix becomes, now what? Let's see what it becomes. The first row remains unchanged, so I just write its values as they are, you see, but the second row and the third row have their values changed in the meanwhile with respect to the elementary row operations we have just performed. So for the second row, we got 0 right over here, and we got 10, and what we have here, 2 times -6 is -12, and adding it 4, we got -8, and we got 6 in the last entry of the second row. And for the third row, we got 0 here, and again we got 10 here, and -8 right over here, and in the last entry of the last row we have 6. Alright guys, now I'm done with the first step of the Gaussian elimination method, since now I eliminated the values below the first pivot element. Now I pass to the second step. So the second pivot element is that the very first non-zero element in the second row, which is 10 in this case. So what should I do? I need to eliminate the values below the second pivot element as well. So this value in the third row, which is 10, should be 0. Okay, how can I do that? Again, I need to perform another elementary row operation, and then I need to replace row number 3 by something else, and just add row 3 plus, if I subtract row 3 from row 2, then I will reach to my goal. So -1 times row 2 would give me the desired results. So let's see what we got. So let's see what we have in the end. Okay, we have 2, we have 4 here, -6, and we have 2 here. Okay, and the values in the second row remain unchanged in the meantime, because we have not performed any elementary row operations on that row at this time. So just write its values as they are, and 6 over here. But if you notice that we got all zeros in the last row, so well, let's write their values. Alright. Alright guys, now this is the second step. Okay, let's recap again. After we are done with each step, we just remember where we started and where we reached so far. Okay, the first thing we did is we just represent our system in the coefficient matrix, not in the augmented matrix, as I noticed you, as I warned you about that actually. And the second step is I reduced my coefficient matrix to either row echelon form or reduced row echelon form, and in this example I applied Gaussian elimination method, and I converted my matrix into the what is known as row echelon form. And am I done with my Gaussian elimination method? Yes, I am done, because in the first row I have no 0, in the second row I have 1 0, and in the third row I have more than 1 zeros, which is enough to say that we have a strictly increasing number of zeros from top to bottom row, and that ends up our elimination process. So you notice that we have this row echelon form. And before going on with the solution, okay, before even pass to the third step, we should look for, let me get one thing straight. You know, in the beginning I said that we may have trivial solution. This is a possibility. We can only have a trivial solution for a given homogeneous system, but if we have non-trivial solutions, then it means that we have infinite number of solutions. And as we all remember from the very previous lectures, we have three different options. We either have no solution, but not in the case of homogeneous systems. We can have either unique case where we have only solution, and we have the case where we have infinite number of solutions, right? Infinitely many points that satisfy all the equations. And how can I understand that? Based upon this end of the actually second step, when we are done with this Gaussian elimination process, we have an infinite number of solutions. Well, it is simple to observe that. Just take a closer look at the very last row. So what we have found, you know, this is something like 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 is equal to what? Is equal to 0, right? We didn't write it, but we know that there is a right hand side value of 0 on the right hand side of each equation. But what this means, no matter what the values of xi's, x1, x2, x3 or x4, multiplying by zeros will give us all zeros on the left hand side, and on the right hand side we have another 0, so which means 0 is equal to 0. But this is a very certain thing, that right, this is absolute. 0 is equal to 0. It is satisfied for all values, which signals that we have an infinite number of solutions, because regardless of the values of unknown variables here, this equation absolutely is satisfied by all the values. In other words, if the values of unknown variables range over all possibilities in real numbers, then they would absolutely satisfy, okay? So just examining through the rows, or in other words, what we have found in the end of the elimination process, we can understand whether or not we have an infinite number of solutions. And if you run into a row which has all of its entries equal to zeros, then this signals us that we have an infinite number of solutions in this case. Alright then, after reminding you this important observation, let's continue with our computational step. And in the third step, now what we need to do. Alright guys, the thing is this. We know that there is an infinite number of solutions. In other words, an infinite number of points, right? Unknown variables that satisfy all of the equations simultaneously, but we don't know what is the form of this general solution, right? So we need to somehow construct a general solution. In other words, we need to find a form of the general solution. And how can we do that? The third step is this. We find the rank of the system. So find the rank. And find the rank means what? Find the rank. We know what the rank is. So how can we find the rank? We reduce our given matrix into a either row echelon form or reduced row echelon form and just count the number of non-zero rows, right? Or the number of pivotal positions or the number of basic columns that we have learned in our previous lectures, and this is the rank. And first of all, let's find the rank and then determine why it is important for us in this step. Alright, so what is the rank? So what I need to do is just I look at the very last matrix, right? The row echelon form. How many rows are non-zero? So we have just two rows that are non-zero, right? The first row is a non-zero row and the second row is a non-zero, but the third row is a zero row because all the values are equal to zero in the third row. So we have two non-zero rows. Or in another way, we count the number of pivotal positions and we have the pivotal position in the first row, 2, and we have the second pivotal position. In other words, the very first non-zero element in each row, in each non-zero row actually, is called the pivotal position, right? The pivotal element. So we have two pivot elements. Or the number of basic columns. And what is a basic column anyway? A basic column is the column of this matrix that corresponds to the pivotal position. Since we have two pivotal positions in the first row and in the second row, our basic columns are the first column and the second column, right? So we know that. Alright. Let's get back. Okay, so our rank is what? Our rank is the number of non-zero rows is equal to 2. Alright, we found the rank, so this is the third step. But why this is important? Actually, what we are interested in here is not only finding the rank, but using it to decide something different, to decide the number of basic variables and the number of free variables. Okay. So this is the fourth step, okay? Let's apply this computational process in a step-by-step manner, okay? So find the number of basic variables. So we have some terminology here, right? Basic variables. So in the solution of a homogeneous system, actually we have two types of variables. One is the basic variables, one is called the basic variable, and the other one is called the free variables. So I'll come to that point soon. Free variables, and how we can decide how many free variables or basic variables we have and what are these variables, okay? And here's the formula that we would stick with. And if we have rank, so if the rank is 2 here, you see, in the general formula is we have n minus r free variables. So the number of free variables is equal to n minus r, okay, number of free variables equal to n minus r, where n is the number of unknown variables, okay, n is the number of unknown variables, and r is the rank of the matrix. Alright then, in our case, in our example, so what is the number of free variables? Okay, we have 4 unknown variables, right? And we have the value of rank is equal to 2. Then we have what? We have 2 free variables. Okay, we have 2 free variables. And how we have found this value? we just subtract the value of rank from the number of unknown variables. So we have 4 unknown variables in our system: x1, x2, x3, and x4. And we have our rank equal to 2. We have just found, right? We just found above. So we just count the number of non-zero rows in this matrix, in the row echelon matrix, and then, which is 2 of course, and then put the value here. So we have 2 free variables. And then how many basic variables we have? So we have 4 unknown variables and 2 of them are free variables, and therefore the remaining 2 variables are the basic variables. So we have also 2 basic variables. So we have 2 basic variables. All right. We have 2 basic variables. All right, guys, this is the fourth step. We decided the number of basic variables and free variables. But what is a basic variable and what is a free variable? Okay, let's get to that point. Okay, and the basic variables, actually we know that each column here in this echelon form, right, each column is associated with the unknown variable, right? So the first column actually corresponds to the coefficients of the first unknown variable, right? So the first column actually represents the coefficients of the first unknown variable in each equation. So it's just like the coefficients of x1. And the second row represents the coefficients of the second unknown variable x2, and the third column represents the coefficients of the third unknown variable x3, and the fourth column again corresponds to the coefficients of the fourth unknown variable. All right, so in other words, each column actually represents one of these unknown variables. So, and here's the thing, the basic variable is the variable that corresponds to the basic column. And what is the basic column? Basic columns are those columns that include the pivotal elements, and in your example the first and the second columns are the basic columns, right? So the fifth step is decide or determine, let's say determine the basic and free variables. Basic and free variables. We know how many of them are there, right? So we have 2 free variables and we have 2 basic variables. And how we have obtained these values? We just compute n minus r, where n is the number of unknown variables and r is the rank. And we find the value of rank equal to 2. And we have 4 unknown variables, so 4 minus 2 is 2. And we have 2 free variables. And since we have 4 unknown variables in total, subtracting 4 from 2, we have 2 basic variables as well. Now we know the number of free variables and the basic variables, and it is the time to decide what these values are, or who these variables are. And basic variables are those that corresponds to the basic columns, and free variables are those variables that correspond to non-basic columns. Okay, and we know how to find the basic columns and non-basic columns based upon the previous lecture. So a basic column is nothing but the column that includes a pivotal position, And here in our example, in the row echelon form, we have the first column and the second column as the basic columns, since we have the pivotal positions in those columns. And we have two non-basic columns, right? We have actually the third column and fourth columns are the non-basic columns. So the third column and the fourth column correspond to the free variables. In other words, x1 and x2, x1 and x2, x1 and x2 are the basic variables. So we decide which of these unknown variables are basic variables and which of these are free variables. x1 and x2 are basic variables. Why? Because they correspond to the basic columns, the columns that include the pivotal positions. And the rest of the unknown variables are the free variables. So x3 and x4 are nothing but the free variables. Why is that? Because they correspond to the non-basic columns. And non-basic columns are those columns that do not include the pivotal elements. Okay, so x3 and x4 are free variables. And this is the fifth step. Alright guys, and in the sixth step, okay, let's continue with our procedure, with our algorithm. So in this step, what we need to find? Alright, as I mentioned earlier, we need to form the structure of the general solution. Okay, now we have free variables, and as the name suggests, they can range over all possible values, and we have the basic variables. Okay, so the thing is, we know with respect to the previous lecture, we can write the non-basic columns in terms of basic columns. This is possible, right? So in other words, we can write the basic variables in terms of free variables. And we can do the same thing to produce the form of a general solution as well. But before even that, first of all, we need to apply back substitution method to write the basic variables in terms of free variables, right? Apply back substitution method, as we are familiar with from previous lectures. So apply back substitution method. Apply back substitution method. Okay. In the row echelon form, okay, method. Okay, in the row echelon form, of course. For what? To write basic variables as a linear combination of the free variables. In other words, I will write the basic variables as an algebraic sum of free variables. And how can I do that? Let's see. So in the last row, I have no chance because 0 is equal to 0. So there would be no coefficient for the unknown variables. But in the second row, you see what we have. We have 10, minus 8, and 6. Okay, 10, minus 8, 10x2 minus 8x3 and 6x4 is equal to 0, right? So here's the thing, guys. If you notice, now x2 is a basic variable and x3 and x4 are chosen as free variables. So what we need to do in the sixth step is, by applying back substitution method, we just write the basic variables as an algebraic sum of free variables. In other words, we have what? We have 10x2 is equal to, if we move this x3 and x4 to the other side of the equality, to the right hand side, we got minus 6x4 plus 8x3. And dividing by 10 on both sides, of course, on the both sides of equality, we divide the unknown variables, the coefficients of unknown variables by 10. We have x2 is equal to right, minus 6 divided by 10 yields us what? Yields us, after of course cancelling out the values, we got minus 3 over 5 x4, right? And we got 4 over 5 x3. Right, here is the thing. Okay, this is actually the first algebraic sum we obtained, right? Let's number it with 1. Okay, let's label it, give some number to it to avoid confusion. Okay, by applying back substitution method, you see in the second row, guys, we got this algebraic sum. So in other words, I write the basic variable x2 in terms of basic variables x3 and x4. But how about x1? So we also have x1, right? So I need to write x1 because x1 is also a what? A basic variable. So I need to express x1 as an algebraic sum of free variables which are x3 and x4. And how can I do that? Now I also have the first row, so I will use it, right? We got 2, 4, minus 6 and 2. So let's write them down. 2, 4, minus 6 and 2. And let's write the unknown variables. We got 2x1 plus 4x2 minus 6x3 and plus 2x4 is equal to 0. So guys, we know that x3 and x4 are free variables, but x2 is a basic variable, so I need to write x1 only in terms of free variables, and therefore I need to move all of this to the right hand side. But while doing so, let's say 2x1 is equal to, alright, 4x2, and this is minus 4x2 when I move it to the right hand side. But instead of x2, I know what it is equal, right? I can write x2 in terms of other free variables x3 and x4 as I just found above, and I number it with 1, right? So I write it down. So what I have is multiplying minus 4, we got 12 over 5 x4 and minus 16 over 5 x3, and let's continue, and what, and plus 6x3 and minus 2x4. all right, so now what we get, we have x3s right here and here, we have x4s right over here, so I just put them together to see what we have, because I need to write them as an algebraic sum of x3 and x4. So I bring x3 and x4 together by simply adding their corresponding coefficients. So we got what? We got, in the case of, okay, here let's do our algebraic operations right here, right over here. So 12 over 5 minus 2. So we got 12 minus 10 is equal to 2 over 5. So 2x1 is equal to 2 over 5 x4, right? And for the x3, so 6 minus 16 over 5, right? We just add their coefficients, their corresponding coefficients for the unknown variable x3. So again, let's multiply the numerator and denominator by 5, yields us 5 times 6, 30. 30 minus 16 is equal to 14, and we have what? We have 14 over 5, 14 over 5 x3. And since the coefficient of x1 is 2 here on the left hand side, we need to divide both sides by 2. So we got x1 is equal to, dividing by 2 yields us 2 over 10. Actually, when 2's are cancelled out, we have 1 over 5 x4, right, plus 14 over 10, and again cancelling out by 2's, we got, it was because 14 over 10. Now what we have is 7 over 5 x3. In other words, guys, what we obtained here, you see, we write the other basic variable x1 in terms of the free variables x3 and x4, so number it with 2. Alright, let's recap what we have found so far, guys. It might seem to be a little confusing, but if you follow up the steps with me, you can understand clearly how we can find the solution. The first step, we just represent our system in the coefficient matrix form, and then reduce our system to the row echelon form. And then with respect to the row echelon form we have just obtained, we find the rank of this matrix, which is 2 in this case, and then we find the basic columns and non-basic columns, and therefore we decide what the free variables and basic variables are and how many of them are out there. So we have 2 free variables and 2 basic variables. Why? Because the number of unknown variables is equal to 4, and our rank is equal to 2. So we have 4 minus 2 free variables. Okay, so 2 free variables and 2 basic variables, because the remaining unknown variables must be the basic variables. So we have 2 kinds of variables. And how we decide which one are the basic ones and the free ones? Of course, the unknown variables that correspond to the basic columns, right, are the basic variables, and the unknown variables that correspond to the non-basic columns are the free variables. And the basic column is the column that includes the pivotal elements, right, the pivotal positions. And the non-basic columns are the columns that do not include the pivotal elements. And in our case, x1 and x2 are the columns that includes the pivotal elements, and therefore the variables that are associated with that column number are the basic variables, which are x1 and x2 in our case, and x3 and x4 of course would be free. And then we apply back substitution method in order to express the basic variables as an algebraic sum of free variables, and actually we obtained our desired result here. So we're done with that. And now what is the following step? Okay, let's say 7. In the 7th step, now we're almost done, guys. We're almost done. Actually, you know what is the solution? And the solution is nothing but a 4 tuple, right? And for the sake of simplicity and a much more clear and easier representation, let's write our solution in the column matrix form. So okay, here's the thing. Now this is x1, right? We are looking for, and this is x2, and this is x3, and this is x3, sorry, and this is x4. This is what we are looking for. So we are trying to find this solution, right? If we find this 4 tuple, then we are done. And I just changed the way I represent the solution. Well, why I'm doing this? Because it would be more convenient to express this solution as an algebraic sum of the free variables, because we need to form the structure of general solution. And by saying general solution, I mean this combination, this sum. Okay, how can I do that? I know x1 and x2 are basic variables, and I write this term, these unknown variables, in terms of free variables. So let's write them down. For x1 is, I numbered with equation 2. x1 is nothing but, let's write it this manner, 7 over 5 x3, right, plus 1 over 5 x4. And the second variable, the second unknown variable, is also a basic variable, so I replace it by its algebraic sum in terms of free variables, right? This is what we have found above here. I numbered it with equation number 1. So I write this. In other words, we have what? We have 4 over 5 x3 minus 3 over 5 x4, right? Let's continue. How about x3 and x4? Well, as the name suggests, these are free variables, so I just put them as they are. So I write x3 and x4, and this is the magic behind the solution of the homogeneous system. Now if you take a closer look at what we have found here in this matrix, which is the solution set, actually we now only have x3s and x4s, right? So how about writing them as an algebraic sum as we did above? So how can I do that? Well, it is simple. We have 2 free variables, right? So how about this? We will be trying to find something else. So a matrix, so by the way, we have a 4 by 1 matrix, and you know, we should stick with the size on the right hand side as well. So again, this should be a 4 by 1 times x3, if I write it this manner, right? And again, something else here times x4, then I'm done. Okay, how can I do that? Well, this is the first column, right? Can write it this way, and I can use this one as the second column. So how can I write it? So I can just plug the coefficients here, right? So 7 over 5, right? 4 over 5 and 1 and 0. So if you notice that if I multiply each term by this coefficient, actually x3 and x4 may seem to be unknown variables for us, but they are just the coefficients of these matrices, right? Because you write them as an algebraic sum, and this x3 and x4 unknown variables are actually any kind of real numbers, right? So they range over all possibilities, so they are free. That's why they are called free variables, right? They can take on any real value. So if you notice, we have 7 over 5 x3, 4 over 5 x3, 1 x3, and no x4 here. And for the other one, now we can just write the coefficients, what is left. Just write down the coefficients that is left behind. So 1 over 5, the coefficient of x4, and minus 3 over 5, right? And since we have no x3, let's make it 0. And we need to have 1 x4, right? So the coefficient is 1. And if you notice again, if you multiply this x4 value by all these coefficients in the matrix, then actually we have this matrix. So there is no change in the solution set. I just write the solution set as an algebraic sum of free variables. So I again have 7 over 5 x3 and 1 over 5 x4 in the first row, and 4 over 5 x3 minus 3 over 5 x4 in the second row. And as you notice, only x3 in the third row and only x4 in the fourth row. So it is just an illusion of decomposing our solution into pieces where we can write our solution as an algebraic sum of the free variables. And in this case, since x3 and x4 are the free variables, then we're done with our solution. And what we have found here is that what is called the general solution of the system. And one thing before ending up this lecture, guys, this is called the general solution. And if you notice that what we have found is actually, we have two free variables, but what if we had many more free variables? Doesn't matter. Our general solution, say the x is our general solution, and the general solution of a homogeneous system should be in the form of something like this that I will be writing on the right hand side of the equality sign. So it is something like, say xi's are the free variables and x1 times, say this c1, and c1 is just a matrix that we used here, you see, right? And x2 times c2 and blah blah blah. Say if we have k number of free variables, then we have, right, a k term in this algebraic sum, in this combination of these free variables. So we have ck, right? So our general solution is nothing but an algebraic sum that has this form. So here again, the unknown variables x1, x2, and xk are the free variables. So if we have k different number of free variables, we have x1 blah blah xk. And what are these ci values? c1, c2, and ck's? They are just matrices, right? They are just matrices. So we have also, well, coefficients and the matrix, and we use them to express our general solution as an algebraic sum. Okay, one simple observation to make before end of this lecture. You see, x3 and x4 are free variables, which means that they can take on any real values. In other words, their values range over all possible values in the real set. Okay, in the set of real numbers actually. So what I mean by that? So before even that, these matrices are called particular solution. So we have general solution and we have particular solution, and this is a particular solution. Okay, so say C1, and this matrix is also a particular solution, and since they are solutions, they need to satisfy the equations. And how can I understand that? It is simple to understand. the way to understand that is if I take one of the values, if I take the value of one of the free variables equal to 1 and the other one equal to 0, right? So say for instance, let's say x3 is equal to 1 and x4 is equal to 0. So what I have, when I plug these values in this general solution form, if I take x4 is equal to 0, multiplying by 0 yields 0 in all entries, and summing up that yields us only x3, right? Because the coefficient is 1. So this should be the solution. What I assert here is that we call them particular solution. Each of this matrix is called a particular solution, and let's write it in a more clear manner. So 7 over 5, 4 over 5, 1 and 0 is a solution, right? In other words, it satisfies the equation. And if we take conversely, in this case, I take x3 is equal to 1 and x4 is equal to 0. I could have done the reverse way. So I could have taken x4 is equal to 1 and x3 is equal to 0. Then what I get? Then another particular solution, right? This matrix is also another particular solution, which means 1 over 5 minus 3 over 5, 0, let's write it down, 0 and 1, right, is another solution. So this means that if I put these values in these equations above, right, in the system, I reach to the desired result. So it is simple to see that, right? If they are solutions, just put these values and see that they really satisfy the equations. Alright guys, so this is the way actually we find the solution to a given system which is homogeneous. And there is some terminology here. Okay, so let's recap our algorithm again. If we are given a homogeneous system where all the right hand side values are equal to 0, the first thing to do is that represent our system in the coefficient matrix form and then apply one of the well-known techniques, either Gaussian elimination or Gauss-Jordan method, to reduce our coefficient matrix into either row echelon form or reduced row echelon form. And after doing so, find the rank of the row echelon form or the reduced row echelon form matrix. And why do we find the rank? Because we need to decide the number of basic variables and the free variables and then determine what these variables are. Okay, we have n minus r free variables, where r is the rank and n is the number of unknown variables. In our example, we have 4 minus 2, in other words, 2 free variables and 2 basic variables. And then determine the basic and free variables, who they are, okay? In our case, x1 and x2 are the basic variables. Why? Because they correspond to the basic columns. And x3 and x4 are the free variables because they correspond to the non-basic columns. And the basic column is a column that includes the pivotal element, whereas the non-basic column corresponds to the columns that do not include the pivotal position. And after deciding which one are the basic variables and which one are the free variables, we apply back substitution method in our row echelon form matrix to express these basic variables as an algebraic sum of free variables in order to form the structure of the general solution, right? So we have x1 and x2, which are basic variables, and then I write x1 and x2 in terms of free variables, x3 and x4. And after doing so, then in the last step, I form the structure of general solution. So we have 4 tuple. Our solution is represented by a 4 tuple. And I plug the values I found above, right? Because I find the equations that correspond to the basic variables in terms of free variables. And then by simple matrix algebra, I just take out the free variables outside the matrix as if they are some coefficients, some real coefficients, and write down the particular solutions in the matrix form. And in the end, I have a general solution form such as x1 times c1 blah blah xk times ck, where xi's are the free variables and ci's are the particular solutions. And a particular solution also need to satisfy each equation, right? So when I take all of the values of all of the unknown variables besides only one equal to 0, and then if I take the remaining one equal to 1, then I have the coefficient matrix right to the left of free variable, and they need to also satisfy the equations. Alright guys, that's it for this lecture, and I hope you enjoyed this video. And in the next lecture I will continue with some examples to show you how we can find a solution. And until then, have fun and see you in the next lecture.